Opening music stops, spotlight focuses. Hello everyone, welcome to today's Tech Talk. I'm your name. In the next few minutes I'll introduce a latest breakthrough in computer vision, RF-DETR Keypoint, a real-time, end-to-end keypoint detection model released by RoboFlow. It surpasses today's top models in both accuracy and speed, and more importantly it solves many pain points that have long plagued developers. Today we'll lift the veil and see how it redefines real-time pose estimation and keypoint detection. This talk has 5 parts. First, we'll review the background of keypoint detection and analyze challenges facing mainstream techniques. Then we'll highlight RF-DETR Keypoint's 3 core advantages, what sets it apart. After that, intuitive performance comparisons will show its industry leadership. We'll briefly explain its technical principles and discuss real business value. Finally, we'll summarize and look ahead. Before diving into the new tech, let's clarify what keypoint detection is. Simply put, it lets computers act like humans, not only recognizing what object is in an image, but precisely locating its key structural points. For a person, those are the nose, eyes, shoulders, knees, and so on. This technique underpins many advanced applications, from motion sensing games to athlete movement analysis to factory automated inspection. Its core value is providing precise location and pose information, the basis for higher-level understanding and interaction. Although keypoint detection is widely used, existing techniques are far from perfect. They face 3 core challenges. First, many top models rely on a hidden hyperparameter hand-measured from COCO. When we apply the model to our own data, that parameter fails and accuracy drops sharply. Second, traditional models give only a coordinate, never telling us how reliable it is. Imagine an autonomous car treating a blurry keypoint as certain, the consequences are unthinkable. Finally, we constantly trade off speed and accuracy, and must maintain multiple models for different scenarios, greatly increasing development and deployment complexity. To solve these pain points, RoboFlow launched today's star, RF-DETR Keypoint. This is more than a new model, it's a new way of thinking. Its design philosophy makes models smarter, easier to use, and more powerful. It has 3 revolutionary advantages. First, a self-calibrating loss that adapts to any dataset with no manual tuning. Second, pioneering usable uncertainty estimates so we know the confidence of every prediction, and third, thanks to NAS training, unprecedented dynamic scalability. One model meets needs from low latency to high accuracy. Next, we'll break down each highlight. RF-DETR's first revolutionary advantage is its self-calibrating loss. Remember that hidden hyperparameter? RF-DETR throws it away. Traditional models need us to say, a localization error should be tolerated within 1 pixel, but HIPs within 5, very inflexible. RF-DETR instead uses a probabilistic approach. Rather than a single point, it predicts a region, a probability distribution. By observing training data, the model learns on its own. Eyes are annotated tightly, so my prediction range should be small. HIPs vary a lot between annotators, so my range should be larger. This is fully automated, letting the model transfer seamlessly to any custom dataset and greatly lowering the barrier to use. The second advantage turns uncertainty from an ignored byproduct into a core asset. RF-DETR outputs not just coordinates but an ellipse representing uncertainty. This ellipse is very useful. First, it intuitively tells us how confident the model is. A clearly visible joint gets a small ellipse, an occluded or blurry one gets a large ellipse. Second, this uncertainty can be used directly by downstream systems in object tracking. A Kalman filter uses it to predict the next position more accurately. In critical decisions, we can trust only low uncertainty keypoints. Surprisingly, the model itself uses this uncertainty to refine final results, gaining extra accuracy. Our experiments prove this uncertainty is highly reliable. When it says 68% probability, it really happens about 68% of the time. Enough theory, let's look at a picture. See the on-screen comparison. Left is a traditional model's output, all key points marked with same-size circles, impossible to tell which is more reliable. Right is RF-DETR's output, each key point has an ellipse. The batter's clearly visible head gets a tiny ellipse, very certain. The crouching catcher's occluded, blurry hips get a very large ellipse, I'm not so sure here. Even better, for fully occluded joints like the catcher's behind the back arm, the model gives not just a position but a dashed line. I inferred this, it may be blocked. For off-screen parts like the umpire's cutoff arm, the model simply doesn't predict, judging the keypoint not found. This rich information is something traditional models cannot provide. RF-DETR's third advantage is its amazing dynamic scalability, thanks to weight-sharing neural architecture search. Simply put, during training we don't let the model learn just one fixed structure, we let it see thousands of different structures. The resulting single model file is like an all-rounder. Need fast runs on low-power edge devices? Just lower the input resolution and it outputs at high speed. Need high-precision cloud analysis? Raise the resolution and it delivers top accuracy. No extra training needed. This means developers no longer maintain multiple model versions for different scenarios, greatly boosting dev efficiency and deployment flexibility. So how does RF-DETR achieve all this internally? It's based on the powerful transformer architecture. Unlike traditional methods, it has no slow heat map post-processing. In the decoder it processes two kinds of queries in parallel: instance queries that find all people in the image, and keypoint queries that locate each person's keypoints. The two tasks finish in one computation and reinforce each other. If an object's keypoints form a plausible human shape, its person confidence rises. This end-to-end joint learning makes the whole model more efficient and accurate. Theory aside, data has the final say. This chart is the gold standard for keypoint model performance, the Pareto chart. Horizontal is speed, left equals faster, vertical is accuracy, up equals better. The ideal model sits top left. The yellow dots are the popular YOLO26 pose family, each an independently trained model. The purple smooth curve comes entirely from RF-DETR's single model file. By simply adjusting input resolution, it moves anywhere along the curve. Clearly, RF-DETR achieves higher accuracy than YOLO26 pose at almost every speed tier, with a very clear edge in the high-value region. Let's look at concrete numbers. At 576 by 576, RF-DETR's preview model reaches 71.8 AP in just 9.8 milliseconds. By comparison, the largest YOLO26 model scores only 71.0 at slightly slower speed. RF-DETR is both fast and good. Push resolution to the max 888 by 888 and RF-DETR's accuracy jumps to 74.2 AP, very close to the academic top model group pose, which cannot run in real time at all. Speed? RF-DETR needs 25.9 milliseconds versus group pose 360 ms, over 13x faster. This fully shows RF-DETR's huge performance edge. Beyond technical leadership, RF-DETR shows great sincerity on licensing. Some widely used models, like the YOLO family, use AGPL 3.0, meaning if your commercial product uses it, your whole product may need to be open-sourced, which many companies cannot accept. RF-DETR uses the very permissive Apache 2.0 license. You can freely use it in any commercial project, including closed source, without exposing your code. This greatly lowers the barrier and legal risk for firms adopting state-of-the-art AI, letting real innovation reach the market faster. After all this, you must want to try it. Good news, RF-DETR is very easy to use. In just 3 steps you can run it on your own machine. First, import the model from the RF-DETR library. Then initialize it, it auto-downloads pre-trained weights. Finally, call predict with your image path. That's it. The results include not just traditional bounding boxes and keypoint coordinates, but also the visibility, discoverability, and uncertainty covariance we discussed. We've provided the full codebase and tutorial on GitHub, try it after the talk. We've used human pose as the example, but RF-DETR does far more. Its goal is any type of keypoint. Robotic arm joints, shopping cart structures, surgical instrument tips, RF-DETR handles them all. Its self-calibrating loss and NAS optimization make it a powerful model generator. In the future, via the RoboFlow platform, users just upload their dataset and the system auto-finds the best architecture for their data and business, then trains it. This will fundamentally change how AI apps are built. Let's wrap up. RF-DETR Keypoint is a revolutionary model combining high performance, intelligence, usability, and flexibility. It excels on benchmarks, but more importantly, it solves real problems that have long plagued developers and lowers the barrier to AI. Looking ahead, the RoboFlow team will keep improving the model, release versions across more performance tiers, and through platform services let anyone easily create their own optimal Keypoint model. We believe this technology will spark new waves of innovation across industries. That concludes my talk. Thank you all for listening. We're now in the Q&A session. Feel free to ask any questions about today's content and we'll discuss together.